Welcome to section 4.1, which is on factors and multiples. We're going to start off by just defining what a factor and multiple is, and then we'll jump into how do you actually find them and use some different models and pictures and blocks to find them. So in this box here, I just copied the book definition of what a factor and multiple is. So let me give you some examples though in my own words. So let's say, for example, we want to find the factors of 16. So if we want to find the factors of a number, we want to find the numbers that go into that number or divide into it evenly without a remainder. So factors of 16 are numbers that divide into 16 evenly without a remainder. So numbers like 1 is a factor of 16, 2 is a factor of 16, 3 is not a factor of 16 because it doesn't go into 16 without a remainder. There are more factors of 16. Another way to draw this out would be to do what I call the rainbow factors. And the rainbow factors, this is just a catch term that I use to, cue students that they need to find the rainbow pairs and do this diagram. I learned this from a teacher many years ago, and I saw her do it in an elementary school classroom. It was a 4th grade classroom at the time, and I just thought it was a really great way of having them list factor pairs and always, ensure that they were not going to forget one because it's easy to do. So the way it works is you start with 1 and you ask yourself, okay, does 1 go in into the number? Well, it always does. So you start with 1 and the number itself. So 1 times 16 is 16. So 1 and 16 are factors of 16. So you draw this rainbow to show that these are pairs with each other. And then go up from 1. So check 2. Does 2 divide into 16? It does. 2 times 8 is 16, so 8 must also go into 16. And then keep going. 3, is 3 a factor? It is not, because it doesn't divide into 16 without a remainder. 4 is a factor of 16. 4 times what? Well, 4 times 4. You can list 4 once or twice if you want to actually draw the rainbow there. But then at that point, we're done, because 5 doesn't go into 16. And then 6 and 7 don't either. So we've listed all of the factors, and by starting with the first number 1 and going to the number 16, we've ensured that we've covered all of our bases. We've gone through all of the possible numbers. So the factors of 16 are 1, 2, 4, 8, and 16. So we've got 5 factors for 16. Now we can say this in there's a couple different ways that we can refer to a number being a factor. So for example, we could say that 2 divides 16. We could say 2 is a factor of 16. We could say that 2 is a divisor of 16. We could also say that 16 is a multiple of 2. Okay, so we're using a different word now. So these are all factors. These numbers all divide or divisors of 16. Well, 16 is also a multiple of all of these numbers. So what is a multiple? Let's list out multiples of 16 over on the left. So multiples of 16. So a multiple of a number is a number that you get by taking a number and multiplying it by anything. So I'm going to start just by multiplying 16 by 1. You get the same number, 16. That 16 is a multiple of itself. 16 times 2 is 32. 32 is a multiple of 16. 16 times 3 is 48. 16 times 4 is 64, and we can keep going. And let's ask the question, is there ever a point where you cannot find any more multiples? Like, is there an end here? And the answer is no. You can always keep going. Whenever you think of a big number, there's always a bigger one that you can think of. So there are infinitely many multiples. There are a finite number of factors for every number, though. Numbers have different numbers or amounts of factors, but there's only so many factors for each number. So if you want, you can check out below where it says content standards. This kind of spells out all of the, this is a 4th grade standard for Common Core of what a student needs to know. So they need to gain familiarity with factors and multiples by finding all factor pairs. Okay, by factor pair, I mean like 1 and 16 is a factor pair. And they need to be able to do it for any number in the range of 1 to 100. So for example, 84 is in that range. They should be able to find all of the rainbow factors for 84. They should recognize that a whole number is a multiple of each one of its factors. So for example, 16 is a multiple of 16, of 8, of 4, of 2, and of 1. It's a multiple of all of its factors. It's also students need to determine whether a number in this range 1 to 100 is a multiple of any given number. And then last, they need to be able to determine if a number is prime or composite, and we'll do that a little bit later. So for this next part, let's talk about how you can use linear models. So there are rods called Cuisenaire rods that are really nice actual physical blocks that, that students can use in the classroom if you're lucky to find a set. If we were in the classroom right now, I would be using those with you. But there's some pretty great videos that we can watch online to see what these blocks are. So let's go check, we'll check out this link. So you can see here in the notes that I've got a rod size 32. Every rod has a different color. And so to find the factors of 32, you would go and find all of the different rods that you could combine together to make a rod that's exactly 32. So for example, the rod that is length 4, you could put 8 of them together and you can make 32. So this is really simple for kids. I mean, it definitely is better if you have the actual blocks in front of you to be able to see how to do this. But just imagine, you know, kids aren't so much thinking initially conceptually about this, but they're just looking at all of the different shapes and lengths of rods and putting them together and finding the same length, which is a really simple way to start this. Another website that's handy too is this one right here. So we can just click on that link. And what this allows us to do is we can actually, I'm going to click the grid so we get that off. But what we can do is we can make our own rods. So for example, let me actually, instead of using 1, I'm going to do a bigger one. So like 10, for example. If I want to find all of the factors of 10, I would examine the other size rods that I could use to make 10. So for example, let's pick a number that I know is a factor of 10. So 5. So if I took out the rod that was 5, I could put 2 of those together and end up making 10. So that shows me that 5 is a factor of 10. Now, if I were to take a rod that's not a factor of 10, so say 4, for example. So kids might say, all right, I'm going to take the 4 rod and see if I can put those together. You can see that there's no way to take the 4s and make a 10. So it's either too short or it's too long. So, and you can keep going. You can see that the 1 is going to work and the 2 is going to work and the 5 is going to work. And so you can go through those like that. So the other method is the rectangular model. So we talked about this with multiplication and division. And we said that, you know, anytime you have a rectangle, if you multiply the lengths of the rectangle, 12 and 7, you're going to get the answer is going to be the area on the inside. So the dimensions of the rectangle, 12 and 7, are factors of 84, and then 84 is a multiple of 7 and 12. So just, you know, remember factors and multiples are just another way of looking at multiplication and division. So let's do a couple of examples. So example A, illustrate that 3 divides 9 with a linear model. So let me go back to that virtual website. So if I'm going to go and find the 9 rod. So here's the 9 rod. And it says show that 3 is a factor of 9. So I'm going to find the rod that's length 3. And I'm going to just put it right underneath. And I'm going to stack the 3's together until I make a 9. On the paper, you could just draw a picture that looks like this. So you could draw, we could say this is 9, and then you could show a 3, a 3, and a 3 together that make the 9 like that. The second example, illustrate that 15 divides. You know what, we're actually getting ahead of ourselves. Let's check out this box right here. So this symbol, anytime a number divides another number, we write it with this vertical line. So A divides B is written like this, or 4 divides 16 is written like that, or 2 divides 8. So if we want to illustrate 15 goes into 45 with a rectangle model, 15 is going to be one of the dimensions, 45 is going to be the area. So if 15 goes into 45, it means 15 is one of the dimensions. So 15 times what gives you 45? Well, 15 times 3 gives you 45. So one of the dimensions is 3 and one is 15. So I'm going to pick 3 goes on the shorter side and 15 is going to go on the longer side. Okay, so this next example, example 2, the directions aren't there, but these are going to be, these are true, false. So let's go through these and say whether or not these are true or false. So 15 divides 60. True. So 15 goes into 60. We know that 15 times 4 is 60. 8 divides 30. False. If we divide 30 by 8, 8 goes into 30. Well, we could go into it 3 times. 3 times 8 is 24, and we have a remainder of 6. Anytime there's a remainder, it's not a divisor. So this next one, 3 is not a factor of 19. True. 3 doesn't go into 19 evenly. 18 is a factor of itself. True. 18 times 1 is 18. And then this one, this is definitely one to think about. Is 2 a divisor or a factor of 0? A lot of times students initially just say, well, no, because it just seems like a weird concept, but think about it. So over here we said, yes, 18 is a factor of 18 because 18 times 1 equals 18. Or over here, 15 times 4 equals 60. Well, let's ask the same question here. Is there a number that we can multiply 2 by to get 0? There is. 2 times 0 is equal to 0. So we say true. 2 is a factor of 0. You can divide 0 by 2. And another way to write this would be 0 divided by 2. And remember in the division notes, I talked about how a fun way of remembering what's okay and what's not is to think of okay and no. So it's okay to have a 0 on the top or to divide a number into 0. It is not okay to be the other way around. So we would not want this scenario. We would not want this scenario. So if we said, if there was a question that asked, is 0 a factor of 2, the other way around, you would say false. 0 is not a factor of any number, okay, because 0 doesn't hold any value. So this next part, odd and even numbers, let's talk about what it means to be an odd and even number. I mean, we've all heard this many times, but it's good to revisit the definition. So what does that mean to be an even number? Well, an even number is a number that has 2 as a factor. So that's why we're talking about it in this section. We've talked about factors. What does that mean? If 2 is a factor, it means 2 divides evenly into that number. And there's some rules that we can learn. One of them is down here, and we'll get to all of these rules in a minute. But if a number is even, it's ones digits, so it ends, the number ends in a 0, 2, 4, 6, or 8. And that's really handy because if you have a big number like 3,246, for example, as long as the last digit is even, 0, 2, 4, 6, or 8, then you know that the entire number is even. Okay, so let's do an example. Would a person oh, there's a typo, with the following license plate have purchased gasoline in the odd number, even number days? Oh, and you know what? I forgot to read this part. You can read this more thoroughly, but basically, Oregon adopted an odd and even system to ration gas. So you could get gas on even days if your license plate was an even number, and you could get gas on odd days, which would be the other numbers that are not even, numbers that are not divisible by 2, if your license plate was odd. So this example asks, would this person, this person had purchased gas on an odd or an even number day. So let's look at the license plate. 1080. What kind of number is that? Well, it ends in a 0. So I just mentioned we have this rule that if it ends in 0, 2, 4, 6, or 8, it's even, which is true. If you wanted to just double check, you could even divide the number by 2. Use a calculator or do it by hand. 2 goes into 10 5 times. Bring down the 8. 2 goes into 8 4 times. 4 times 2 is 8. Bring down the 0, it goes into 0 0 times. So it's divisible by 2 without a remainder. So you would say they would go on the even days because that's an even number. So there are a lot of different ways that we can test whether or not a number is divisible by another number. So if you have a calculator, this process is super fast because you can just take your calculator and divide it to figure out if it's a factor. So for example, if I wanted to know if the number 52,689 was divisible by 3, all I'd have to do is divide it by 3, and I'd see that I got a whole number answer, and I'd say, yes, it's divisible by 3. So that's great if you have a calculator. If you don't have a calculator, there's some of these divisibility tests, we call them. They're basically like shortcuts that allow us to more quickly tell if a number is a factor or not. So I'm going to go through, I'm not going to read these all because you've got them in your notes, but I'm going to go through the examples on the next page, and then we're going to revisit these rules as we need them. So example 4, these are all true false. We're trying to see if these numbers are factors or not. So for A, is 2 a factor? Does 2 divide 248? So let's go to the rule up here. So for 2, a number is divisible by 2 if its ones digit is 0, 2, 4, 6, or 8. So I'm going to say yes, it's divisible by 2 because the number ends in 8. So this is an even number here. So we're going to say true. 2 goes into 248 because that last number is even. So like on a test, for example, if you were asked this question, all you'd have to do is write, or even just do what I did here, point to the 8 and say yes because that's even, then we know that 2 goes into the number. So the next one, does 5 go into 346? Well, what do we know about 5? 5 goes into a number if and only if its ones digit is 0 or 5. So that basically means, does the number end in a 0 or 5? It has to. So this number does not end in a 0 or 5. It ends in a 6. So we're going to say false. Does not end in a 0 or a 5 would be the explanation. For C, a number is divisible by 10 if and only if the number ends, the ones digit is a 0. So that's also listed up here in the divisibility test for 10. So if and only if its ones digit is a 0. So this number, last number, is a 0. So we say true, 10 does go into 2,370. Okay, so let's move on to 4. So what's the rule for 4? So a number is divisible by 4. We've got that right here. If and only if the number represented by the last 2 digits is divisible by 4. So what that means is you could have a really long number like 3,482,625, and if you didn't have a calculator, all you would have to do is look at the very last 2 numbers and say, well, is 25 divisible by 4? It's not, so this number is not divisible by 4. It makes it a lot quicker. So let's go look at our example. Okay, so 897, instead of dividing that by 4, we're just going to look at 97. So is 97 divisible by 4? That's all we have to figure out. So I'm going to take 97, 4 goes into 9 2 times. 2 times 4 is 8. Bring down the 7. 4 goes into 17 4 times, but I'm going to have a remainder. So we're going to say false. 4 does not divide 97, so it can't divide 897. Okay, so the next question asks about 8. So let's go check out the rule for 8. So a number is divisible by 8 if and only if the number represented by the last 3 digits is divisible by 8. So like that last example, let's say I have this number 3,459,800. All I'd have to do is look at the last three and say, well, is 800 divisible by 8? Yes, it is. So this entire number is divisible by 8. So let's look at our example. I'm going to look at 846, and I don't know just off the top of my head if that's divisible by 8. So over here, I'm going to divide by 8. Now, you might be saying, okay, this isn't fast. Well, it's not super fast, but it might be faster than, well, and it will be, than the 2,846. So it saves us a little bit of time. 8 goes into 8 once. 8 does not go into 4. Bring down the 6. 8 goes into 46 5 times. And you're left with a remainder. So you're going to say false because 8 doesn't divide 846, so it can't divide 2,846. Okay, so the next one, we've got 3 and 9. So the rule for 3 is that a number is divisible by 3 if and only if the sum of its digits, so sum means add up all the digits, and the sum must be divisible by 3. The same is true for 9. You have to add up all the digits and see if they're divisible by 9. So let's go and do the next two examples. So for F, I'm going to add up the digits 1, 2, 3, 4, 5. That's 12,345. I add up all of those digits, and if I add them up, I get 15. 3 goes into 15, so I'm going to say true. 3 must go into 12,345. Let's check 9. So it's the same number. So if I add up all these digits again, I'm also going to get 15. So 9 does not go into 15. So I'm going to say false. 9 is not going to go into 12,345 because it doesn't go into 15. So that saves me some time there. So the most complicated one is 11, I mean. So the rule for 11, you can read it if you'd like. It's a little bit confusing in words, but I'll show you how to do it, and hopefully that'll clear things up. So basically, a number is divisible by 11 if it divides the difference, so difference is subtraction, of the sum of the digits whose place values are odd powers of 10 and the sum of the digits whose place are even powers of 10. Okay, this is where the confusing part comes in. Basically, what this is saying is you just need to add up every other digit, and we're going to find the difference. So we're going to start with 1, 3, 0. So I started with the last number, and then I'm just skipping. I'm going every other, and you keep going until you run out of numbers. So I'm going to add up 0, 3, and 1. 0 plus 3 plus 1, and I end up getting 4. And then let me get a different color. I'm going to add the other numbers together. So 9 plus 9 plus 8, and I get 26. Okay, so I found the sums of those digits. Then I'm going to find the difference of those sums. Difference means subtract. It does not matter what order you go in. So you could do 4 minus 26 and get negative 22. You could do 26 minus 4 and get positive 22. The negative is not going to matter either way. So now the last part is you want to figure out, does 11 go into negative 22? Can you multiply 11 by something to get negative 22? Yes, 11 times negative 2 is negative 22. So that's true. So this whole problem is true. 11 does go into this number. Now you might say, well, gosh, it might have been easier to do long division. That may be the case, and you can certainly try that, but it's a fun rule to just try. And this would be one I would say, like if you were doing with some fourth graders, this might be a challenge problem for them. So let's do the next one. This would be a great place to pause the video and try it on your own. I'm going to identify every other number, 7 plus 5 plus 3. So 12 and 3 is 15. And then I'm going to look at the other numbers. So 6 and 4. So sometimes you don't have the same amount of numbers. Just depends how big the number is. Okay, and then I'm going to find the difference. 15 minus 10 is 5. Does 11 go into 5? No, it does not. So you're going to say false for this one. 11 is not going to go into 76,543. And then last but not least, 6. So if you look above, a number is divisible by 6 if and only if both tests for divisibility for 2 and 3 hold. So let's go back and review those. A number is divisible by 2 if it ends in 0, 2, 4, 6, or 8. So let's check that. out for the number that we're looking for. And then it's divisible by 3 if the sum of its digits is divisible by 3. So let's go look at our example. It ends in an even number, so we know that 2 goes into, so the rule for 2 is satisfied. So to check if 3 is a factor, we're going to add up all these digits, and we end up getting 28. 3 does not go into 28 evenly, so we're going to say 6 is not a factor of 324,856. So we're going to say false for this one. So both the 2 rule and the 3 rule have to pass. You can't just use one, it does not suffice. So 6 does not go into that number. And if you're ever not sure, just use your calculator. So divide 324,856 by 6 using your calculator to see if if you're right or not. So you've got tools to help you with these. And then last but not least, so this one is a challenge problem. So find the smallest counting number that is divisible by 2, 4, 7, 6, and 12. Another way of thinking of this problem is what's a number that 2, 4, 7, 6, and 12 go into? Great place to pause the video and try this. One thing that I'm thinking of right now is I know that 2 goes into 12, I know that 4 goes into 12, and I know that 6 goes into 12. So if I just use 12, I don't have to use the 2, the 4, and the 6 because those by default, if I pick a number that 12 goes into, then 6, 4, and 2 are automatically going to go into it because they go into 12. So for example, 24. 12 goes into 24, so does 2, so does 4, and so does 6. So I don't even have to worry about that so much. So really what I need to worry about is I need to look at the 7 and then the 12 and ask myself, what are some multiples of 7 and what are some multiples of 12? So 7 times 1 is 7, 7 times 2 is 14, 7 times 3 is 21, 7 times 4 is 28, 7 times 5 is 35, 7 times 6, 7 times 7, 7 times 8, 7 times 9, 7 times 10, 7 times 11, 7 times 12. Okay, and we could keep going. Sometimes with these, you don't really know when to stop. So my advice is just, go however long you think, and then you may need to go some more. So with 12, we've got 12, 24. 12 times 3 is 36. 12 times 4 is 48. 12 times 5 is 60. 12 times 6 is 72. So I'm looking for a number that they both have in common as a multiple. So far I don't have any. 12 times 7 though is 84. Is that a coincidence? Not really, because 7 times 12 is 84. So it makes sense that 84 is going to be a multiple of both 7 and 12. So 84 would be the smallest number that is divisible by 7 and 12. And then we know that it's also divisible by 2, 4, and 6 because 12 goes into that number as well. So not exactly a short solution, but that's a great way to map it all out. Okay, so next part, we're going to talk about prime and composite numbers. So this next part, example 4 asks to use base 10 blocks to make as many rectangles as possible for the following numbers. So I don't have base 10 blocks in front of me, but basically what this is asking is if you can imagine, for instance, like a unit block. I'm asking you to, if we were doing this in person, to take 10 blocks, 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm sorry, not 10 blocks, base 10 blocks, but in this case we're using 16. So 1, 2, 3, 4, 5, 6, 7, 8, and make a rectangle. So this would be one rectangle. Pretend this is actually straight, so it would look like this. One rectangle, that's a possibility, is 2 by 8. That shows that 2 and 8 are factor pairs for 16. We can list out the other ones. We already did 1 and 16. So what would that rectangle look like? It'd be a 1 by 16 rectangle. Our other factors would be a 4 by 4. Now notice a 4 by 4, this is a square. So anytime you have a square number like 16, which means a square number is a number that has a perfect square root to it, you're going to get square factors. So those would be the factors for 16. If we listed out the factors for 30, we would get 1 and 30, 2 and 15. So if you wanted to draw the rectangles, a rectangle that'd be 1 by 30, 2 by 15, 3 and 10, okay, 5 and 6. Down here is the definition for prime and composite numbers. So a prime number is a whole number with exactly 2 factors, and a composite number is a number with more than 2 factors. I want to really highlight this definition. I don't know about you, but when I went to elementary school, I learned a different definition. I learned the definition that a number is prime if and only if the only factors are 1 and itself. So this is kind of the same. It's very similar, very, very similar to the definition that a number has exactly 2 factors, because you look at this 1 in itself and you say, okay, well that's 2, right? The only problem though is the number 1. So if you think of the number 1, how many factors does 1 have? 1 has 1 factor. 1 goes into the number and itself. So if you use this definition, you would almost look at 1 and you'd say, oh, well, 1 is prime because it has factors 1 in itself, so that works. The problem is that 1 is not prime, and so you don't want to use this definition of 1 in itself being the only factor, because it leads you astray when it comes to the number 1. So think of this definition only as a prime number has exactly 2 factors. So the number 1 only has 1 factor, not exactly 2. So we say 1 is neither prime or composite. Okay. Let's go ahead and actually list out some prime numbers, and we're going to use this chart below. So let's go through all of these numbers and we're going to list out the factors, so numbers that go into these numbers. So the number 1 has a factor of 1. 1 goes into it. There's 1 factor there, and we're going to say neither, because remember, prime numbers have only 2 factors and composite has more than 2. Okay. 2, what numbers go into the number 2? 1 goes into 2 and 2 goes into 2. So 2 has 2 factors, so we're going to say this is prime. 3, 1 goes into 3, 3 goes into 3. So there are 2 factors there, so 3 is prime. 4, let's think of the rainbow factors. So 1 and 4 goes into 4, and then 2 and 2. So 4 has 3 factors. So since that's more than 2, we say 4 is a composite number. 5, 1 goes into 5, 5 goes into 5, and that's it. So that has exactly 2 factors. So 5 is not C, we're going to write P for prime. 6, 1 and 6. 2 and 3. So 6 has 4 different factors, so it's considered composite. 7, 1 and 7, so there's exactly 2 factors, so 7 is prime. 8, we've got 1 times 8 is 8, 2 times 4, so there are 4 different factors, so this is composite. 9, 1 times 9, and then 3 times 3. So there are 3 different factors for 9, so 9 is a composite number. So 9 is an odd number, but it's composite. 10, 1 and 10, 2 and 5. So 1, 2, 5, and 10. So there are 4 factors for 10, so that's composite. 11, only 1 and 11, so exactly 2 factors. So that's prime. And then 12 is 1 and 12, 2 and 6, and 3 and 4. So we've got 1, 2, 3, 4, 5, 6 factors, and that's composite. So really, if we look at this list, we're looking at any of the numbers that have exactly 2 factors are the numbers that are prime. So we're looking at 11 as a prime number, 7 is a prime number, 5 is a prime number, 3 is a prime number, and 2 is a prime number, okay? So it might be helpful. You could definitely list these out, and I'll list them out down here. So prime numbers would be 2, 3, 5, 7, 11, and I'll actually list out a couple more too: 13, 17, 19, 23, 29, dot, dot, dot. It's helpful just to have a list to get you started. So let's look at example 6 and answer these questions. So will there be numbers other than 1 with only one factor? So think about that for a minute. Can you think of another number that would only have one factor? The answer is no. All numbers have 1 and itself as a factor by minimum, okay? So all other numbers are going to have at least 2 factors, if not more. What kinds of numbers have an odd number of factors? So let's look at this list. I'm going to use a different color here. So let's look at the number of factors list. So this list right here. So we're looking down here, and let's look at which ones are odd. So 1 is odd, 3 is odd, 3 is odd, okay? What kinds of numbers are those? So we're looking at 1, 4, 9. So 1, 4, 9. Think about those in terms of a block, so what does that look like in terms of a rectangle? So if we have 1, you could do 1 times 1 gives you 1. To get 4, you could do 2 times 2. To get 9, you could do 3 times 3. So what are these numbers called? These are called square numbers. So any numbers that have a square root are going to end up having an odd number of factors, because when you do the rainbow pairs, there's going to be a number that goes with itself. So for example, if you think of the number 4, 1 goes with 4 and then 2 goes with itself. For 9, 1 goes with 9, 3 goes with itself. Whereas the other numbers, like 6 for instance, these all pair up together. Or 12, these pair, and these pair. They're distinct pairs. So those will all be even number of factors. And then lastly, are there numbers with more than 6 factors? What do you think? The answer is yes. There are numbers with more than 6 factors, because think about it, the numbers don't ever end. So numbers can get bigger and bigger and bigger and bigger. And so there are infinitely many numbers with very large amount of factors. So there's no limit there. So example 7, we're going to continue this chart listing prime or composite. So let's list the factors for 13. So we got 1 times 13. So we're going to say prime there. 14 would be 1 and 14, 2 and 7. So I'm going to say composite. 1, 15, 3 and 5. So I'm going to say composite. 1, 16, 2, 8 and 4. So that's going to be composite. 1 and 17. So this is prime. 1 and 18, 2 and 9, 3 and 6. So that's composite. 1 and 19, prime. And then we've got lots of factors here, 4 and 5. And so that's going to be composite. So we're adding to our list here. So we said 13 was prime, 17 was prime, 19, and I listed those up here, and then I also added a couple more. So, and down here where it says the prime number is less than 21, you can just kind of look at this list here. The reason why I wanted to list out all the prime numbers is because there's this neat little test. It's called the prime number test, and it helps us determine if a number is prime or not by using a shortcut. And here's why we want a shortcut. Take this example, 421. If I asked you, is 421 prime or composite, and you didn't know a shortcut, what would you do? One option is to take your calculator, and you could take 421 and just start dividing it. So you know it's divisible by 1, but divide it by 2. Okay, it's not divisible by 2. And then you do 421, and then you divide it by 3. Oh, let me go back. So 421 especially if you're using one of these calculators. It's not liking my fingers today. 421 divided by 3. Okay, you get the idea. So it's not divisible by 3. It's not, you could check 4 and 5 and 6, and basically you keep checking to see if there are more than 2 factors. The problem with this is you could be here for a really long time. I mean, the number is 421. So, you know, you're not going to stop until you get to 421. It could take you a while. One method is to use, it's called the prime number test. And what it says is that you find a number, a whole number, the smallest whole number, such that when you multiply it by itself, it's greater than the number. And then once you find that number, you only have to check the primes that are less than that. So for example, 421. Think of a number that when you multiply it by itself, you get close to 421. So an example might be 20 times 20 equals 400. So in one way you could start this is just by taking the square root. So if we go back, we could do 421 and we could take the square root of it and we get around 20. So that gives us an idea of where to start. So let me hide the calculator here. So we know that 20 squared is 400. Let's do 21 squared. If you do 21 squared, you end up getting 441. So this rule, we're trying to find a number that when you square it, it's greater than the number. So 21 squared is 441. That's the number that's going to be bigger than 421 because 400 is not bigger. So this means that we have to check up until 21. So check out this list of prime numbers here. We are going to divide 421 by all of those numbers until we get to 21. So you're going to take a calculator and you're going to, I'm not going to go through all of this, but you're going to divide 421 and you're going to divide it by, we already did 2, where you're going to divide it by 3. And then you're going to do 421 and you're going to divide it by the next prime number, which is 5. And then that didn't work. And you're going to divide 421 by the next prime number, which is 7. Whoops. And you're looking to find an answer that's a whole number. Oh my gosh, this calculator. All right, I'm going to stop because this is giving me all kinds of trouble, but hopefully you get the idea. So 421, you're going to keep dividing by all of these numbers until you get to 21. So you'll go through 19, and if none of them go into 421, then you say it's prime. And with this number, this does end up being prime. None of those numbers end up going into it. Okay, for 667, okay, so I am going to bring the calculator out real quick. You're going to do 667, and let's find the square root. You end up getting around 25. So that gives us a place to start. So I'm going to say, I'm going to figure out, well, what is 25 squared? 25 squared is 625. That's not quite big enough. 26 squared is 676. That's just bigger than 667. So I'm going to check all the prime numbers until 26. Now 26 isn't a prime number, so the number that's closest would be 23. So I would take 667 and divide it by 2, 3, 5, 7, 11, all the way up to 23 and see if any of those work. And 23 ends up going into 667. So this is actually a composite number. And then last but not least, with 211, you could take the square root of 211 and it ends up being between 14 and 15. So 15 squared is 225. So it's just bigger than 211. So you're going to check all prime numbers up until 15. So that would be actually up until 13 because 15 isn't prime. So you'll divide 211 by 2, 3, 5, 7, 11, and 13. None of those are actually going to work. So at that point, you can just say prime. And I know this might seem cumbersome, but oh my gosh, it saves you so much time because you wouldn't be able to stop at 15. You would have to keep going all the way to 211 if we didn't have this rule. So that's the end of 4.1. We'll see you next time for 4.2, where we talk about greatest common factor and least common multiple.